Right, so let's look at some sequences and series questions, specifically geometric series. So it shouldn't really be anything too difficult. Part A is just asking you to prove the standard result, which you should have practiced numerous times before, but it's just to double check that you know how to do it. Parts B, C and D are then just applying it. And this would be a typical sort of question that you might need to know the answer to when it comes to geometric series. So give it a go. Pause the video now. Okay, so first question. You've been told that Sn is equal to the following sequence: A plus AR plus AR squared dot 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 plus AR to the n minus 2 plus AR to the n minus 1, and n minus 1 is the final term, because effectively this is our 0 term, this is our 1 term, and this is our n minus 1. Therefore we've got n terms in total, which is what we need. The trick then to coming up with this expression, trick you should be familiar with: multiply both sides by r. When I multiply both sides by r, I'm going to get the following. I'm going to deliberately leave a bit of a space, a bit of a gap, just to make clear what's going on here. Dot 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 plus, so I suppose I'll still get that, I'll still get this, and I'll also have this one now on the end as well. Okay, so effectively that A has become AR, that AR became AR squared, so forth, so on and so forth, and the AR to the n minus 1 became AR to the n when I multiplied by r. Then we're going to do the top expression, expression 1, minus the bottom expression, expression 2. So what does that give me? It gives me Sn, the sum to n terms, minus r times Sn equals, and in this case that AR and that AR will cancel, these two cancel, all the stuff in the dots cancels, and the only thing I'm left with is A minus AR to the n. And that I can rewrite like this. And on the left hand side I'm going to factor out Sn, so now we've got this. And then finally dividing by both sides, 1 minus r. And we've got what we were expected to get, the equation for the sum to n terms of a geometric sequence. Okay, so this question here then is just testing that we can employ this correctly. Let's just make a note of the formula again. So as is always the case with a series, if you've got a constant on the inside, no point keeping it in there. Let's take it to the outside. Makes things a bit simpler. Okay, and sometimes it's helpful to write the sequence out a little bit by hand. So that is to say, this is 2 plus 2 squared plus 2 cubed plus dot dot dot. Okay, so then this is going to be, oh sorry, I shouldn't say dot 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 like that, because that implies to infinity. So I should make it clear what the end point is in this case. It's when k is 10. Okay, so it's just the first 10 terms. Right, so, or we could alternatively just call it S10. Okay, so it's 100 times S10. In this case, then, what are the key values of the formula? A is the first value, is 2 in this case. The common ratio is also 2, because we're multiplying by 2 each time, and the number of terms is 10. Putting that all together, 2 times 1 minus 2 to the 10, all over 1 minus 2. Okay, so let's see what that gives us. That gives us 200 times 1 minus 2 to the 10 all divided by -1. So I suppose we're just going to get minus here. But then to deal with that minus, we can just flip what's going on in the brackets. We can turn it into this. Okay, and at that point, you'd bring out your calculator. So I'd get 2 to the power of 10 minus 1 times 200, and we end up with 204,600. And yes, that is indeed the answer. Okay, and then part 3, nice and simple. You've got the sum to infinity of a geometric series. Technically, this third term is completely unnecessary, but if you've been told it's geometric, you can take it on faith that the ratio is the same each time. However, I suppose as a sanity check, they've given you 3 terms rather than 2. What do I multiply 5/6 by to get 5/18? It's a third. And then check that that makes sense. 5/18 also times a third gives me 5/54. Okay. The first term, A, is 5/6. The common ratio, R, is a third. The sum to infinity of a geometric sequence, or a geometric series even, is A over 1 minus R. Therefore, we've got 5/6 all over 1 minus a third. And we end up with 5/4 as our final answer. Okay, and then part D is just a very quick check. The most succinct way to answer this question is as follows. It's effectively 5 strokes of the pen. The modulus of R has to be less than 1. You might sometimes see it as this, but the first expression is a lot more succinct and expresses exactly the same thing. So this ultimately just stems from, just as a reminder, if we go back a little bit to, where are we? Here. Seeing as this is the sum to n terms, if I'm saying n goes to infinity, then r to the n must be not getting bigger as n goes to infinity, because if it was getting bigger and bigger and bigger, then my sum to infinity is not going to converge to a finite number. So that little r must be such that as n goes to infinity, r to the n goes to something smaller and smaller. And that will only happen when r is a fraction, specifically a fraction between -1 and 1, not inclusive. Okay, and that answers our part D. The modulus of the common ratio must be strictly less than 1.